please.
I'm going to try to speak loud because I know that these things on the phone, they don't work as well. So I'm going to present today quantum computing in the energy industry. This is a line of research which we do at Total. Let me perhaps briefly tell you a bit about myself. I'm Marko Rancic. I'm leading the quantum computing efforts at Total. Since some 2 years ago, Total started heavily investing in quantum computing as a continuation of efforts in high-performance computing, which we had. I joined Total a bit more than a year ago from Switzerland, where I lived and worked. The project which I manage is a multi-million euro project which develops algorithms for quantum computing. By background, I'm a theoretical physicist. This is in short about the project itself. And the more technical really aspect, the more non-technical aspects about the project. Now I dive into the technical part of it. So first, let me tell you why do we do research in quantum computing in Total. We identified strategic directions in which quantum computers are beneficial for Total. This is to start with its optimization, differential equations for physics, or general for fluid dynamics, to be honest, modeling of chemical systems and materials, and there is something we call combining quantum hardware and software, which I'll also touch briefly. So what are the main challenges in the optimization domain? Well, we really made a strategic decision to be carbon neutral in Total until 2050. So this our goal to be carbon neutral requires us to invest in technologies how to achieve that. And as you probably heard today, one of the biggest, if you want, use cases for early days quantum computers are the optimization use cases. And basically, where we use optimization, we really use it in order to optimize the movement of our fleet, or in order to think of distributing the electric car charging stations and things like that. In the what we call chemistry line of research at Total, this is not really chemistry. Only this is chemistry and material science. People, somehow it's common not to differentiate between the two. In chemistry domain, we're really big with CO2 capture. We do have a large line of research within quantum computing to model materials for CO2 capture, and this part of our research is actually even EU funded, so we even got some external financing for that between the NASQC consortium, which kicked off a few days ago. On top of that, we are actively modeling or starting to model battery electrode materials and solid-state batteries with quantum computers. I'll touch a bit this later. And we have a plan to investigate a bit more catalysis for CO2 conversion, but we still aren't there really in the catalysis domain. Then the next use case which we have is basically solving equations for physics. And most of you know that basically solving the differential equation on a quantum computer is a tricky business because of the level of hardware that is required to do that. So current day NISQ quantum computers are not really able to do that. So basically what we are doing, we are really this is a long planned line of research which we have. This is something which we plan to do up front. We're really trying to estimate resources required to solve PDEs of interest for Total when somebody makes a universal fully error-corrected Turing machine. And last but not least, this is a line of research which is not really about writing scientific papers. It's about combining all of the really quantum hardware and quantum software we have basically available to us. This is a number of our partners. With some we have a collaboration in place. With some we negotiated collaborations. With some we just openly exchange. So we don't have a signed contract really with everybody who you see here. Probably our premium partner, if I'm allowed to say this, is Atos. We are basically in synergy with the Atos team. We purchased the Atos 35 qubit simulator device, and all of our researchers are really heavily involved in Atos machines. Okay, let me give you an overview about what my broad research project is about. This is the broadest sense, the list of partners which we have. So I'm based in Paris region, and you see it's pretty heavy in Paris region itself. This is a shift. We really wanted to increase the number of partners we have in Paris. There's Atos, Sorbonne, and there's Fairfax, where we have two PhD students and a postdoc, so two researchers. So with Pascal, we are currently negotiating a partnership. They're an amazing startup from the Saclay Plateau. Here at the University of Leiden, we have two PhD students. We also have a partnership with Cambridge Quantum Computing in the UK. QC, where we mainly interact with them in the domain of quantum annealers. This is not something which I'll be speaking about today because I have just 20 minutes for a really long talk. Also, we spoke a lot with Google researchers about getting access to their hardware, likewise with Xanadu, and we are planning to become a beta tester of Zapata's orchestra platform. Okay, let me now give you a bit of a more scientific deep dive. So now I put my scientist hat. Basically, first use case, this use case, which I'm going to show it to you here, is basically mesh segmentation in general. More, it's basically investigating different graph partitioning algorithms. So here we had an intern called Antoine Hayek, and he investigated the QoA solver, and we are really working hard to expand this line of research. This also line of research was awarded EU financing within the NASQ consortium. The idea behind this is basically to have a computational geometry architectures, which Pascal is making, but also other hardware is possibility, which hardware EU belonging to this EU consortium. What we have here next is more. I want to present another line of research which we are doing in basically combinatorial optimization. What you're seeing here is the figure of one of our PhD students in Leiden, in the Netherlands, in the group of Vedran and Dunko. And basically, what is the idea between this line of research? What he did, he applied classical machine learning techniques and to train a model. When should the QoA algorithm be used, and when should the Gueman-Williamson algorithm be used? And basically, what this gave an accuracy of 96% in just beating the classical approximative Gueman-Williamson algorithm, and in 82% of the cases, it remarkably overperformed with respect to the classical method. This was on the use case of free regular graphs. There's an archive reference here, but it just got accepted to Quantum Science and Technologies 1 or 2 days ago, and we are expanding our research with Vedran and Dunko in Leiden, and basically we started with another PhD student there. So briefly about our chemistry research in things like carbon capture, battery modeling, and lubricants. So what we have now, we have an in-house VQE solver, and we've had it for a while really now, because our idea is not just to be somehow an end user of quantum technology. We are an end user of quantum hardware, of course, but we are not an end user of quantum software. And basically, because of that, we needed to develop our in-house variational quantum eigensolver to help us treat problems of interest to tau. Seeing here, which is called MOF5. This MOF5 material is basically like a filter which we use for carbon capture. The yellow blob, which you see here, is basically a pore. It's a hollow material. It's a porous material. It has benzene linkers connecting gray metallic clusters here. And basically the idea is to apply a quantum algorithm here to fragment the large molecule into small pieces and to use the native parallelization of quantum computing to get a better calculation of the MOF5. And I'm going to immediately go to the next slide. Basically, these are some results from our researcher Elvira Shishania, which are the result of our collaboration with CQC. Basically, we developed a fragmentation tool for treating MOFs. This is an aluminum fumarate cluster of a MOF, and here what you're seeing here in this table, you're basically seeing the ground state energies, where quantum VQE algorithm with a hardware efficient ansatz and a unitary coupled cluster ansatz is compared to the Hartree-Fock and the FCI. This full configuration method. It's the state of the art in quantum chemistry. And you see, and I'm not sure how good you see, but the results really differ in a few percent between classical and quantum. But beware, this is still on quantum simulator. So these are not really results which originated in actual hardware. And we are really working hard to expand further this line of research. Okay, something fuzzy happened with my image here. I hope you can see it better than I can. Basically, what we plan to expand on this further as part of our EU funding, which we got. We also plan to investigate benzene linkers and different metal organic frameworks and different type of materials such as benzene, which is a nice periodic lattice. And this we plan to do with one PhD student, which is starting in early 2021. And we plan to expand this line of research with one postdoctoral researchers, he was going to work on molecular symmetries. Also, a bit more on the future plan side in the material science domain. We have a PhD student which is starting in a few days now, who's going to be investigating high temperature superconductors and battery electrode materials with quantum computing. Focus is going to be lithium cobalt oxide. What is lithium cobalt oxide? You have it in your smartphones. It's the electrode of the lithium ion batteries, and this electrode has a type of a metallic to an insulating transition, which is of a MOF type of an insulator transition. And classical methods really cannot do much beyond DFT to solve this, and the idea is to attack this type of problems with one PhD student, and eventually really to run real algorithms on real algorithms on Pascal's hardware. And last bit about the third line of research, but this is just going to be brief because I'm slowly running out of time. I want to leave some time for questions if there are any. What you're seeing here, you're seeing here the result of our PhD student by name of as well. He works at the CEFAX at Lille, and what he did, he implemented a quantum algorithm for solving PDEs. So it's like a quantum Laplace algorithm. And now you understand why I said that variational algorithms are not really good for differential equations. What you're seeing in the upper figure, you're seeing that there is a certain, like in every variational algorithm, this is the VQLS algorithm, it has a certain cost function. And when the cost function goes to 0, like it does in all of the cases in the upper figure, basically it means that you converge to a solution, that your model converges to a solution. However, when you look at the lower, figure, this lower figure is like a fidelity of the solution. If the lower figure goes to 1, this means that you're in a good solution. If a lower figure goes to 0, this means that you're in a bad solution. And you see that you're all over the spectrum. You have some solutions which are good solutions, some solutions which are bad solutions. What is happening here? The system keeps ending up in local minimas. And this is a big problem of all variational quantum algorithms, but it's especially pronounced somehow in these variational algorithms for basically PDEs or in general linear algebra algorithms. Even on a small toy model, it's like I think a 4x4 matrix, the quantum algorithm ends up in a fake correct solution. And it's quite likely the way situation is currently that really quantum error correction is going to be required to solve PDEs on a quantum computer. And then basically this is what I call transversal collaborations. This I already mentioned, so maybe I'm just going to skip it in the interest of time. Basically, what we're really hoping to do, we're really hoping to run our algorithms on actual hardware, Pascals and Xanadus. We were also speaking with Google, but because of the COVID situation, this potential collaboration got postponed a bit. And what you're seeing on the right-hand side, these are all the partners which Total has in the software domain. I finish with this question. With this slide, our final goal is really to be a recognized player in quantum algorithms in the energy industry. And now I'll gladly take any questions if there's any way how people can ask questions while I'm connected via the phone.
Thank you very much, Marko.